Surface water comes to us from many different sources: streams, lakes, and reservoirs. According to the US EPA, more than one-half of the water provided by community water suppliers comes from surface water. Every surface water supply has its own unique set of characteristics, yet must be treated to meet federal and state drinking water quality standards. Despite these many variations they face, the goal of water treatment operators is always the same: clean, safe drinking water. Even water that looks clear and pristine may contain contaminants that can cause aesthetic problems or pose a threat to public health. One of the most important characteristics operators must evaluate is the source water's turbidity. Turbidity is a general term that refers to the suspended matter or non-settlable solids which can make water cloudy.
If we know that there's turbidity in the water, we know that there's particulates in there. We don't know what those particulates are, but we know that some of those particulates could cause health problems. And so throughout our history as water suppliers, we've been measuring turbidity because it just gives us a general idea of the cleanliness of the water.
These particles may be a combination of algae, plankton, bacteria, viruses, protozoans, organic matter, and inorganic solids such as silts and fine sand. These small particles can cause aesthetic problems such as color, taste, and odors. They can also harbor harmful bacteria, viruses, and protozoa such as Giardia and Cryptosporidium. Not all the particles that make up turbidity are a public health concern by themselves, but they can protect pathogens against disinfection.
Naturally occurring particles, clay and other bits of dirt and stuff, can shield the pathogens from the disinfectant, making the disinfectant less likely to kill the pathogen that you're trying to kill. So it's important to remove turbidity, not just to remove the pathogens, but also to allow the disinfectant to work better.
Because of the aesthetic and public health problems associated with turbidity, water utilities pay close attention to turbidity levels in finished water. The most common method of removing turbidity is called conventional treatment, which is a combination of coagulation, flocculation, and sedimentation followed by filtration. Coagulation and flocculation agglomerate turbidity into larger, heavier particles that can then be more easily removed by sedimentation and filtration. The particles that cause turbidity consist mostly of non-settlable solids. These particles typically do not settle out of water because of two factors. One is particle size. Fine silts, protozoa, bacteria, viruses, and natural organics are microscopic. Non-settlable solids are broken down into three types. Suspended solids, which include fine sand and silt, range in size from 1/10 to 1/100th of a millimeter in diameter, or perhaps smaller. They are held in suspension by the natural action of flowing water. The smallest of these particles don't settle quickly, so for practical purposes are considered non-settlable. Smaller yet are colloidal solids, which measure from 1/1000th of a millimeter, or 1 micrometer, to 1/1,000,000th of a millimeter, or 0.001 micrometer in diameter. These very fine clays, bacteria, viruses, and color-causing particles are essentially non-settlable. Unaided, they would take days or even months to settle out. They must be coagulated to become settleable and filterable. Dissolved solids are the size of a molecule. These trace metals, organic chemicals, salts, and gases cause public health, taste, odor, and color problems. Some can be removed by chemical coagulation. Others may require additional treatment, such as ion exchange, sorption on activated carbon, nanofiltration, or reverse osmosis. The second reason these particles resist settling is called zeta potential. That's the natural repelling electrical force of particles found in water. Most of the particles contributing to water's turbidity have a negative charge. Just as like poles of a magnet repel each other, so do these particles. Zeta potential keeps the small particles separated, suspended in the water. To overcome the zeta potential and increase particle size, operators rely on a chemical treatment called coagulation. Coagulation is the addition of chemicals to destabilize the electrostatic forces of non-settlable solids.
Once you neutralize the charge, they'll be allowed to come together and stick together and form a larger and larger particle that can either settle out or be filtered out.
If you didn't treat them chemically, most of them just would not come out. They'd go right through your filters and go right on.
Coagulant chemicals typically have a positive charge, which binds to the negatively charged particles in water, neutralizing them and allowing them to come together to form small clumps of particles called microfloc. The coagulant chemicals are added to the source water in a process called rapid or flash mixing, which can be achieved in several ways. The most common is with the aid of a mechanical mixer. These can be mounted in a chamber or directly into a pipeline as an inline mixer. Static mixers, pumps, and conduits or baffled chambers can also be used. In most cases, the chemical reaction occurs in a fraction of a second, so it's important the coagulant is dispersed quickly and evenly to encourage as many particle collisions as possible. Because this process relies on chemical reactions, several considerations must be made. First is water temperature. Colder water usually slows coagulation and flocculation reactions. Extreme values of pH, high or low, will also interfere with the process. Water with low alkalinity is less reactive and does not coagulate well. Operators may need to raise alkalinity for coagulation to be effective. Turbidity is also important. The lower the turbidity, the more difficult it is to form proper floc. Sometimes a weighting agent, such as bentonite clay, may be added to increase the concentration of floc-forming particles. Before coagulation can take place, the operator must determine what type of chemicals and at what doses will best treat the turbidity in the raw water source. This is an important step because not only do operators need to treat the water effectively, they must do so in a cost-efficient manner. Coagulant chemicals are typically monovalent, bivalent, or trivalent. Valence describes how reactive an ion is. Trivalent ions, such as aluminum or iron, have more positive charges and more sites to bind negatively to charged particles. As a result, they are 50 to 60 times more effective than chemicals with bivalent ions and 700 to 1,000 times more effective than chemicals with monovalent ions. The most common coagulant chemical used is aluminum sulfate, commonly called alum. When added to water, alum forms jelly-like particles of aluminum hydroxide. The trivalent aluminum ions neutralize and attach to negatively charged particles in water, forming microfloc. Alum works best in a pH range of 5.5 to 7.5. Polyaluminum chloride and iron salts such as ferric chloride and ferric sulfate are alternatives to alum, and they operate over a wider pH range.
The chemists have gotten more creative and they've developed compounds that are advanced in various ways. You can have polymerized aluminum salts, you can have blends of the inorganic coagulants, the alums and the ferrics. They all have their little benefits that will improve the clarification process.
Coagulant aids are added to improve coagulation, build stronger, more settlable floc, overcome the effect of low temperatures, reduce the amount of coagulant needed, and reduce the amount of sludge produced. Commonly used coagulant aids are activated silica, which has proven effective in colder water, weighting agents such as bentonite clay and limestone, when source water has a low mineral content or turbidity, and polymers. Polymers are long chains of molecules that produce highly charged ions and help bind microfloc together into larger floc particles. They have become very popular with operators because they can be positive, negative, or neutrally charged, providing a great deal of flexibility in different circumstances.
Oftentimes people use cationic polymers in the rapid mix area as well, which do something they refer to as particle bridging. You might get a nice alum or ferric floc formed, but it's still fairly small, and so there are organic molecules, polymers, that can be added in small doses that allow them to bridge together. They form bridges across the flocs, which will make them larger and, again, more readily settlable or filterable.
Chemicals are also used prior to coagulation to help the water respond better to coagulant chemicals. Lime, soda ash, caustic soda, and sodium bicarbonate are used to increase the alkalinity and adjust the pH of water. If the alkalinity is too low or pH values are out of range, later changes in alkalinity or pH in treatment or the distribution system may cause flock to reform, causing customer complaints or a buildup of sediment in the distribution system. After coagulation, the water moves to a flocculation basin. The gentle stirring action of flocculation brings the microfloc together in a process called agglomeration to form heavier particles called floc. These larger floc, which look like snowflakes or tiny tufts of cotton, will then settle during the sedimentation process.
You need to add enough energy to the water to gently stir the water so that the particles come together and stick, but not so much energy that they shear apart again. So usually flocculation basins have large either paddles or hydraulic mixing of some kind that's gentle, and that'll allow the particles to sort of clump together and form larger ones that can be settled or filtered out.
As operators monitor the coagulation and flocculation process, there are several key indicators that will suggest some adjustments are necessary. Common problems include low water temperature, weak floc, slow floc formation, and over or under feeding of chemicals. Indicators of ineffective flocculation include poorly developed floc, such as very small floc or pin floc, lightweight, fragile, or broken up floc, high turbidity in settled water, and too frequent filter backwashing. There are a number of tests the operator can conduct to gain information to make the proper adjustments in optimizing the coagulation and flocculation processes. The operator can test the water's pH level, since coagulants and coagulant aids work best in a certain pH range. Turbidity tests should be performed on both the raw and settled water.
That gives you an almost instantaneous view of what's happening with your chemical processes through the treatment plant. And what that helps operators to do is to keep a very close watch of exactly what's going on with the water chemistry.
Sending the effluent through a small pilot filter can test the filterability of the settled water. An instrument called a zeta meter can test the zeta potential of the water. A streaming current monitor gives a continuous readout of the net ionic and colloidal surface charge in sample water. Particle counters operate by passing a fine stream of water through a laser or light source so a computer can determine the size and concentration of minute particles in the water. Particle counters give more information than turbidimeters regarding particle size and concentration, but are more expensive and more difficult to adjust and operate. Visual inspection is also important. Proper basin lighting allows operators to view floc development at critical stages of formation. And finally, jar testing has proven to be very effective. Jar tests are a good way for the operator to examine the chemical dose as well as mixing times and speed. A jar test can simulate the full-scale plant's mixing and settling in a laboratory setting with many possible adjustments under consideration. Once proper floc has formed, it must be separated from the water through sedimentation or clarification. This process takes place in a rectangular, square, or round tank called a sedimentation basin or clarifier. Solid particles are kept in suspension in water as long as it flows with sufficient velocity and turbulence. Sedimentation removes floc by slowing the flow of water through the basin. The heavier floc particles drop to the bottom and clarified water is collected for filtration.
It's all different kinds of sedimentation processes, but generally they all work by gravity. Take advantage of the fact that gravity's free and always works. So generally the water is traveling horizontally and the floc particles are settling vertically. And hopefully the particles settle to the bottom of the basin before the water gets out of the basin.
Sedimentation basins have 4 zones. The influent or inlet zone decreases the velocity of the incoming water and distributes the flow evenly across the basin. The settling zone provides the calm area necessary for the suspended material to settle. The effluent zone provides a smooth transition from the settling zone to the effluent flow area. It's important that currents don't stir up any settled solids and carry them into this area. The final zone is the sludge zone, where settled solids are separated from other particles in the settling zone. There are many variations in design for sedimentation basins. The two most common types are rectangular and circular clarifiers. In a rectangular clarifier, water flows across a rectangular basin. A circular sedimentation basin is fed from the center and water flows to the outer edge of the basin. Plates and tubes may also be used to increase flow rates and enhance settling in a smaller basin. As water travels up through them, instead of having to settle as much as 10 or 15 feet, particles have to settle only a matter of inches to reach the surface of a plate or tube. As particles continue to settle out and build up, they can slough down the tube or plate and eventually settle to the bottom of the basin. There are many alternatives to traditional sedimentation, including high-rate and upflow clarifiers. Some processes combine coagulation, flocculation, and sedimentation into one basin. In an upflow solids contact clarifier, the influent is passed through baffled zones for coagulation and flocculation. The flocculated water then flows upward through the sludge blanket at the bottom of the tank. The existing sludge blanket reduces the velocity of the incoming flock, in effect filtering flock from the water as it travels up through the basin. These variations in design are generally used to reduce detention time, increase flow rates, and raise capacity within a smaller footprint.